In this final module, we tackle the problem of likelihood-based inference. The Gaussian distribution is the building block of parametric statistics. We will start from here to arrive to much more advanced technique such as model-based clustering. First, let's introduce the concept of random variable. We say that y is a random variable if it is the outcome of a random experiment. For example, if y may be the blood pressure taking into account the fact that, due to technical limitation, it will always be measured affected by some level of noise. That is why, measuring it several times, we obtain different values. We model such variability through a statistic or probabilistic model. This is usually defined via some analytical function that depends on some parameters. These parameters are unknown and must be estimated. This process is usually called statistical inference. The most common model in statistics is the Gaussian or normal model. It is particularly convenient thanks to its flexibility and analytical tractability. Usually, most of the mathematical calculation admit an analytical solution, which is very useful in practice. This model is suitable for continuous variables, positive or negative. The figure on the right shows the famous bell-shaped function that defines the Gaussian distribution. It is defined by means of two parameters, the mean, denoted by mu, and the standard deviation, denoted by sigma. The mean mu defines the center of the distribution, while sigma models the variability around mu. In practice, we say that a random variable y is distributed according to a normal distribution with parameters mu and sigma if we expect its outcome to be mu with some possible variations in the range of mu plus minus 2 times sigma. The larger sigma, the larger our uncertainty, while smaller values of sigma mean that we are confident about the fact that y will be equal to mu or very close to it. As I was saying before, we do not usually choose values for mu and sigma, but instead we would like to infer their values. To do so, we need to collect data that we assume to be generated from our statistical model. Then, the key mathematical object we use to perform inference is called likelihood. This is simply the product of the density functions of normal distributions. The function we end up with is a function of mu and sigma, since data yi have been observed, so we have values for them. The inference problem in classical parametric statistics is solved using the maximum likelihood estimator, usually denoted by MLE. The idea is to find a numerical answer to the following question. What is the value of mu and sigma that maximizes the probability of observing values yn up to yn? In mathematical terms, the problem is equivalent to find a value for mu and sigma such that the previously defined likelihood function achieves its maximum value. The previous problem can easily be solved in the case of Gaussian model. Indeed, it is easy to prove that the maximum likelihood estimator for mu is simply equal to the mean of the observations, while sigma is equal to the standard deviation of the observations. The rightmost plot, we have the histogram given by 50 observations generated by sampling from a Gaussian distribution with mean equal to 10 and standard deviation equal to 2. In red, we have the estimated density, which is indeed very similar to the true one. As I was saying at the beginning of this module, the Gaussian model is the building block for more advanced model. The first one we describe is the multivariate Gaussian model, which generalizes previous definitions for multivariate data. We probably never use this word, but multivariate data are something we already work with in the previous models. We simply say that data are multivariate where more than a single feature is observed. For example, whenever we measure blood pressure and heartbeat. Jointly, they form what is called a multivariate sample. The main feature of a Gaussian multivariate distribution is that plotting the collected sample, the cloud of points has an elliptic shape. The shape of such cloud depends on the parameters of the distribution. For simplicity, let's focus on two variables only. This case is known as bivariate multivariate distribution. A bivariate, normal or Gaussian multivariate distribution is characterized by a vector of means, one for each variable, while its variability is defined through a 2 times 2 symmetric matrix, usually called sigma. The diagonal elements define the variability of each variable. The extra diagonal term defines how strongly these two variables interact. Small values in absolute value mean small interaction between the variables. Visually, this is the case when we see that the shape of the cloud of points is circular. Large value in absolute value instead mean strong interaction between the variables. Visually, this is the case when we see that the shape of the cloud of points is elliptical. The final topic we tackle is model-based clustering. To solve the cluster analysis problem, we already met k-means and hierarchical clustering. These are model-free or non-parametric models. We now introduce a third alternative named mixture modeling, which is instead model-based. Similarly to k-means, we need to pre-specify the number of clusters k. There are pros and cons for choosing this approach against k-mean and hierarchical clustering. Mainly, mixture modeling is better when one must find clustering having elliptic shapes, since k-mean and hierarchical clustering favor clusters having a circular shape. We will see a practical example of this situation. The main drawback, instead, is that being model-based, it is less flexible than a non-parametric approach. As a consequence, it struggles when the model is not suitable for the data. For the moment, I claim that it is based on a statistical model without introducing such model. Here, we provide a sketch of it, having in mind that an exhaustive discussion of it is beyond the goal of this module. First of all, we assume that there exist k clusters. Then we model data within each cluster to be Gaussian distributed, eventually being multivariate Gaussian. Finally, we say that each data is assigned to each cluster according to a certain probability called mixing distribution, indicated by pi k. Hence, pi k is the probability of being assigned to the kth cluster. These probabilities are unknown and must be estimated from the data. Moreover, cluster-specific parameters defining location and shape of each cluster, must be estimated as well. Putting all these three information together, we end up with a model that, in mathematical terms, is written as shown in the slide. In the following, we will refer to previous model by calling it mixture model. Inference regarding the unknown parameters is achieved through likelihood maximization, following the same idea of what we saw at the beginning of this module. However, the problem is definitely more complicated than the simple Gaussian model. Indeed, the solution cannot be written in analytical terms. The problem has been unsolvable for many years. Then, a special algorithm called EM algorithm has been developed to solve this problem. Details about the estimation process go beyond the goals of this module. We conclude with a practical example to compare mixture modeling and k-means. The leftmost panel shows some synthetic data which have been generated to represent three different clusters having elliptic shapes. The middle panel shows the final partition obtained using mixture modeling, setting k equal to 3. Cluster analysis is almost perfect. Clusters are almost perfectly identified. In particular, the elliptic shape of the clusters is recovered. On the other hand, the rightmost panel shows the estimated partition obtained with k-means setting k equal to 3. Note that, in this case, the cluster analysis is much worse. Not only the number of misclassified points is higher, but the identified cluster have circular shapes rather than the elliptical ones.